So first I want to finish up, not really chapter 17, technically we finished chapter 17. It was a very complicated one. We know all about k-nearest neighbors now, just the idea of using that distance formula in multiple dimensions to go and find a bunch of things that are similar and pick out the class, because it's a classification problem. Pick out the closest class for this brand new point that we've seen. So essentially that's machine learning, all right? We talked about that. So that's more or less the idea of machine learning. You guys know how to do that now. You guys know how to like train a computer to think new thoughts, like given some data, predict something I've never seen before, predict the class of an individual that I have not yet seen. And so that's us training like a model. We're training a machine learning model, we say, to do some prediction, to like make some inferences for us, to do some cool thing. And that's where we stop. So I wanted to just take a few slides, as I am required to teach it to you. It's part of the class. I'll take 3 short slides to talk about just like the idea of with great power comes great responsibility, because you guys are going to have access to, if you become a data scientist, you're going to have access to a lot of potentially private data, right, that you don't want to get out to anyone. And then also you have to be very careful with the way you use that data, because if you train a machine learning model to do some prediction, to do some things like to generate text or something like that, you have to take care to make sure that that text that it generates is not like mean or bad in some way. So let's talk about the ethics of all this, and like how bias could get involved, and we want to get rid of any potential biases or prejudices in our models, because that might be present in our data, unfortunately. So we need to deal with that. So yeah, ethics is just the study of doing the right thing. You might have to take a class on that one day. Like it's like a critical thinking class. If you take CSI 1, you'll learn a little bit about that in the context of computer science. So that's a fun thing that we offer here. But yeah, let's talk about some things that might go wrong that you're going to need to worry about one day maybe. So just make sure use your skills for good, not for evil. All right. So you, as a data scientist, maybe you have access to people's financial data, people's medical data. Like you're doing something for a bank, you're doing something for a hospital, and there are laws about that data and the way it needs to be kept private, right? So that's important. If you get access to that private data, you need to be very careful about how you like deal with your models. Like you can't take your work home sometimes. Like that's a thing. Like you need to leave your laptop at work. You can't. Maybe you have to sign a non-disclosure agreement, an NDA. Things like that happen. All right. So you can't really publicly post your graphs, your results. Save it just for your boss. Stuff like that. So you have to be very careful about the way you handle what you've discovered and the things you've generated from your private data. So you have to worry about that, all right? So you might have to keep it encrypted, right? Keep it encrypted behind 2-factor authentication, like Canvas for me, but it's going to be more important at like a hospital or something like that. And yeah, make sure to, like, if you're using this data, you're training your model, maybe once the model's finished, you can just delete that data. Then you don't have to worry about it getting into the wrong hands, stuff like that. So that's the thing. So there are different laws that protect data. You'll have to maybe learn those one day, like HIPAA. I forget exactly what that stands for, but we can look it up real quick. That's like the laws that are attached to medical data, right? Health Insurance Portability and Accountability Act. Apparently that keeps your private medical data just yours. And when it gets leaked, there's a problem and people get sued, right? So that's the thing. You might have to learn the laws that go with the data that you're using and training your models with, doing analysis with, stuff like that. And for example, there's another law, FERPA, which I don't also know what it stands for. Your student records are protected by that. So I can't go and, like, even if your mom calls, I can't give her anything. I can't tell her your grade. I can't tell her anything about what you've done in my class. You are protected by that law, for example. Like, I have to know that. Okay? And so that's something that you might have to know one day. All right? Family Educational Rights and Privacy Act. So there we go. That's a thing. Don't remember what it stands for, but I know what I have to do. So yeah, that, like, the school, for example, also, like, when you guys take my class, this is kind of weird because they do this at other colleges, like they did this at UCSB. They told me the majors of the students who I was teaching. I don't even get to see your guys' major. So, like, that's why I asked you on the first week in the check-in survey. Like, I have no clue. So that's kind of fun and weird to think about, but that's something you might have to deal with. All right, so I just want you to keep it in the back of your mind. And here are some sad examples of things that might go on. So here's, I'll just let you read this old tweet of an example of bias in machine learning during the COVID era. Bless you. This is really unfortunate once you get through reading that. And so yeah, this person like was taking a test, and they trained this machine learning model to detect like, hey, are your lights on? Can I see this this test taker in a way that like I can record easily and make sure they're not doing anything shady, because nobody was like, these were like proctored by AI exams kind of things. So yeah, they didn't. It looks like whatever this software was doing, it wasn't really trained very well on different skin colors, and so that's a huge problem. Okay, so hopefully you'll take that into account one day if you become like a machine learning scientist. And then, yeah, let's just talk about, so this is bias in general. Like, so this is your training data was biased towards maybe white people or people with lighter skin color and versus darker skin color. And that's a problem. And then you can also get into bias where you've got some like you're training like a text prediction engine. You can try to read that on the right if you'd like. It's a very sad example of a text prediction gone wrong. So because that's all AI is, right? It's trying to predict the next word, trying to get some like from all of its knowledge that it's learned off the internet. It's trying to like make sentences and form somewhat coherent thoughts, right? And we've used ChatGPT and things like this. This is like the Twitter or X's version of it that was unfortunately not trained with too much data, I think. So you have to like, sometimes you have to withhold some things when you're dealing with machine learning and data science. So like when you make a model, so model, just remember that word is just like, that's the black box that you're training. Like that's your classifier, that's your text prediction engine. Like that's the fancy thing that you spent a lot of money to make. That's going to be representative of your training data, which is the thing that you're using to like make sure the model is working. So if you give it a lot of like, think of Twitter. People are just saying bad things to each other all day long on Twitter, right? So or X or whatever it's called now. So your models are going to be representative of your training data. And so if you're using just all of Twitter, for example, to train a text prediction engine, then your model is going to start saying bad things to people, because that's what people do on Twitter sometimes, in some corners of it at least. And so that's unfortunate. So you might have to get rid of some data. You might have to filter it. And then also you got to make sure that you're not just training on that one corner of the data as well. So don't just train on bad people saying bad things. Train on like the scientists like saying their work on Twitter or something. I don't know. Nice things too. So yeah, if you don't have a lot of data, that's two sides of this coin. If you don't have a lot of data, your model won't say enough things. It won't have enough knowledge. But if you also maybe need to filter it, because sometimes you don't want it to say specific things. Is there a question? Yeah.
Are there any laws to try to get rid of bias?
That's a great idea, and I really don't know. That's too new. I don't know. I don't have that knowledge. I've heard that recently the federal government was trying to pass some laws to regulate the way that states deal with AI. So California AI agent laws. Let's see if there are any. Dun, dun, dun. What is this? Recommendations. AI and privacy. That would make sense. So at least I feel like California is probably leading this. So let's take a look at this real quick. Reshaping the boundaries of privacy and artificial intelligence.
I guess kind of with like marketing or political,
Yeah.
I feel like they shouldn't be allowed to bias that. You know?
Yeah, and I feel like people are going to pay a lot of money to make sure that that is not a law that gets passed. That's very unfortunate. So yeah, are there any laws about bias in machine in AI? Potentially other countries have dealt with this. Maybe the European Union, they like to pass laws that are in that regard, I feel. So that's probably a thing. Laws and regulation regarding bias and artificial intelligence are rapidly developing, but tell me more about it. Okay, yeah, so California prohibit employers from using automated decision systems that result in discrimination. So I feel like that's a good example, maybe, of like a law that helps people. Colorado AI to avoid discriminatory outcomes. So yeah, maybe I'll have to, let me make a note for myself to keep track of that. Maybe next semester there'll be more stuff. But yeah, I think this is just starting. Oh, cool. AI, yeah, the European Union. I remember hearing something about that. Set strict guidelines for AI systems, especially those deemed high risk, to ensure transparency, fairness, and safety. That's interesting. Yeah, so I feel like we're just in the beginning stages of all that, unfortunately. Or I don't know. Maybe you guys can become lawmakers now that you know all about data science. You can sway us in the right directions. So yeah, that's a great question. Any other questions? Any other thoughts I want to discuss? Because this can be a discussion. So yeah, there's two sides of this coin. You got to make sure you got enough data. Like ChatGPT was trained on like all of Wikipedia, all of the internet, all of Reddit, and so like you have all this knowledge, but you also want to filter out any knowledge that is like bad knowledge, like people saying like hate speech on the internet, because that exists, right? You're going to come across that, and you probably don't want that to be part of your training data, because it's just like you're having your machine learning model take in everything and try to remember it all. It doesn't really, it has no ethics itself. You have to give it the ethics. So that's the thing. Okay. So yeah, I think that's all that I really wanted to say about ethics and bias. It's just something to keep in the back of your mind. We've been dealing with Serial and Titanic Passenger. That's not nearly as problematic as it might be one day for you. So that's important to keep in the back of your mind. Yeah. Any questions about that? Thoughts? So yeah, some more somber topic for the day. But yeah, let's talk now, if we're ready, about the last chapter of the textbook, chapter 18. It's nice that they did this at the last chapter, because chapter 17 was a doozy. There's a lot. Chapter 18 is very short. It is to the point. It's a little bit of math. It's not the world's worst thing. And so this probably won't take very long. So yeah, there should be more time to do some stuff. But read chapter 18. It's the last chapter of that textbook. We're almost there. We're almost towards the end. There's not a lot of slides. And so maybe there'll be extra time to work on the last assignments, because these are going to be the last assignments to be released. Homework 12 and lab 10. That's it. That's all we got in the class. So yeah, let's get started with that. So I'm going to teach you this whole topic of this chapter. It revolves around a mathematical idea that has to do with probability. It's called Bayes' rule, if you've heard of it before. If you've taken like a more advanced math class, or maybe I think maybe you learned it in high school. I can't honestly remember. Seems like an algebra 2 kind of concept, maybe. I don't remember. But all right, Bayes' rule. Let's motivate it before I show you the formula and everything. So here, let's say that you transfer to Berkeley, and you're going to get a data science degree. And so you're going to come in, usually you've done like 2 years here, and so you go there and you'd be a third year. All right, but maybe some other students in the class, in the next data science class you're going to take, are going to be second years. They're sophomores at Berkeley, but you'd come in as a third year. So you're sitting in that class. Some people are like you, some people are a year before you. So the class has second years, 60% second years, and 40% third years, because that just happened for that year. And so 60% sophomores, 40% juniors in the class. And you know that 50%, half of the second years, have declared their major. They know that they're going to be like data science. They know that they're going to be computer science. They know that they're going to be math or something. So they've got a declaration of their major. Only half of them. There's still some, like the other half are still figuring it out. They're undeclared. That's something you can be at a four-year college. Can you guys be undeclared here? Is that a thing? You have to pick something. You have to pick. Interesting. I didn't know that. So, yeah. Well, can you take classes here undeclared though? Just for fun?
I'm sure you can do that. Yeah.
Okay. So if you want to,
can't go there as an undeclared major.
That makes sense.
Especially
Okay.
if you're going to community college, you have 2 years.
Yeah.
Really.
Interesting. Yeah. So it's a bit different at a four-year college, maybe, compared to what you guys have experienced so far. So yeah, some people can be undeclared, and let's say that 80% of the third years they've got their life in order, and they've declared their major by then. Only 20% of the third years have not declared their major. And so that's what the class looks like. You know that there's 60% second years, 40% third years. You know that half of the second years have declared their major. You know that 80% of the third years have declared their major. And I flip like a 100-sided die or something, and I have a number for every student. Like I pick one student at random. My question to you right now is, can you use your intuition? Can you do a little math maybe to try to figure out, like, if I pick one student at random with that setup, which is more likely to get a second-year student or a third-year student? Let's see what we're thinking, and maybe we can make this into a bi-clicker question. Like let's say A for second year and B for third year, and I'll start that. But I want you guys to discuss with each other, see if you guys agree, see if there's a way like you can do some math just in your mind or on paper, break out paint, sorry, not attendance, but bi-clicker. But try to enter in like A or B. Do you think it's going to be like that random student? Is it more likely to be a second year student, a sophomore, or a third year student, a junior, given that exact makeup, given those percentages? Can you solve for it? Can you see it? Can you draw a picture maybe? We can have a try. Maybe a couple minutes to think about it, and I'll teach you a way to think about that if it makes it easy. You can use Jupyter to do some number crunching for you if you need to, maybe. But one hint, maybe. I'll give you a couple more minutes though. But like maybe pretend there's exactly 100 students. See if you can use that to break it down. So that'll make the percentages kind of easy. All right, was that enough time? Let's see. Give you another minute. About it. Second year or third year? Let's see. Yeah. That's my timer. All right. Let's see what we're thinking. We think that A is the answer. We think it's second year. So yeah, let's try to figure this out. I think that's fine, right? Does that make sense why it's A? You don't even need to deal with the fact that they've declared their major, do you? Yeah. So yeah, they're 60% of the class. It's like a 6 out of 10 chance that I call on a second year student. This didn't really change anything. But maybe it will, all right? Maybe it will change something. So here's another question, all right? So another scenario, same probabilities. You got second years 60% and third years 40%. All right. And then 50%, you know, second years have declared their major, 80% of the third years have declared their major. And then, all right, you pick a student again randomly, but then you ask them, hey, have you declared a major? And they say yes. Does that change whether or not it's a second year now? Do you see the question now? Do you see how that changes the idea? Because you know that, okay, if they say yes, 80% of the third years have declared their major, more likely, maybe it's more likely a third year, but less of the class is a third year. You see the problem there? So there's something going on that's different and cool. So we need to think about this. It's like you want to count this idea. So like we've got, you know that the class is, let's try to draw this to scale. Boop. Whee. All right. So you weren't tricked by the first one, but this one is a little tricky. Let's see. So, all right, it's not 50, it's 60, let's say. So that's the makeup of the class, kind of. You've got, these are the second years, and these are the third years. It's broken up in that way. And then you know that, let's see, 50% of the second years have declared their major. So like, if I cut the second years in half, I know that 50% of them have said, yes, I have a major. I know what I want to do. 50% have said no, but for the third years, 80% have declared their major. So 50, 75, let's say 80 is right there. 80% have declared their major, and only 20% have said, I don't know my major yet, still. So the question is, if I call a student randomly, is it more likely, and they say that they've declared their major, I know that I'm either in this part or this part. Does that make sense? And the question is, which one's more likely? It has to do like, is this area bigger than this area? Is now the question. They look very similar, don't they? So did it change anything at all? Let's try to figure that out. So we want to know, like, am I here? Am I in this spot or am I in this spot? Which one's bigger? Which one has more area? Let's figure that out together. All right. So, because there are more second years, but fewer of the second years have declared their major. That fact that the student told me they've declared their major changes everything, in a sense. All right, it changes the weights of everything. So the first option to like solve this problem is we can totally write some code. I'll show you that. We'll like simulate this idea. And though there is a mathematical thing that we should learn. So we'll do that later. We'll do that second. But here is the setup. Let's pretend we've got exactly 100 students. All right. That would make it easy on us. So I'm going to do something silly and cool. You can make, I taught you like make array makes an array of things. Like you can say second year, second for second year, and third for third year. But you can't really like duplicate the number set, like the word second a bunch of times. Can I do that? Like second and 5 doesn't really do anything. It's like it makes an array of the string second and makes 5 a string. Sure. You can't multiply this by 5 or like make 5 things in second, but you can do that with lists. So like if I make a list with the square brackets and I put second in it, I am able to, that's just it's still like an array. A list is like an array in Python. It's just like a little bit more primitive. So I can say I want 60 second years by saying, give me a list of just 1 second year, multiply it by 60. That's useful for me. And I can turn that into an array. I can say, I can't say do make array. I can do np.array like we were doing last chapter to turn something that is iterable, some list-like thing, into a array. And so that's what I want. Like here's how I can make very quickly 60 second years where the string involved tells me if they're second year or third year. So I'll make 60 second years, and then I'll do the same with that. I'll add that to 40 third years, right? Because it's if there's 100 students, there's 60 that are second year and 40 that'll be third year. That can be our simulation. So plus third multiplied by 40. So that will make an array that looks like this. Excuse me, thank you. So it'll make an array of 60 of the word second and 40 of the word third. So there's my class that's made up in terms of like what their what their year is, sophomore or junior. So I'll call that year. And I can do the same thing for major, because I know that the first half of the second years, right, are declared or undeclared. So like the first half is declared, the second half of the 60, right? The first half of the 60 are undeclared. So I want to pair up these. I want to make two arrays. I want undeclared times 30, right? For the half of the second year. So I want this to go in order. For the 60 second years, there's 30 of them that are undeclared and 30 of them that are declared, right? So we can do that in that order. So plus 30 that are actually declared. And those will line up with the second years. That's 60 of them so far. And then I can add that to knowing that I've got 80% of the third years that are declared and only 20 that are undeclared. So what in the world is 20% of 40? It's apparently 8. So there's 8 undeclared third years. All right. 8 undeclared third years. And the rest are going to be, so 32 of them, the rest are going to be declared. Does that kind of make sense what I've done? I can turn that into an array. And if I pair them up, because I put them in order, but 60 second years, 40 third years, and then 30 undeclared, 30 declared, those will match up with that's all these guys. That'll match up with the 60 second years, and there's 40 more things. There's 8 undeclareds, followed by 32 declareds. Those will match up with the third years. So if I make those each the columns, right? I can make some students out of that. So that's the major. And then I can make it a table of students now. So like table with some columns of like I've got the year. It's all the things in the year array, and then the major is all the things in the major array. And that can be my array of, I'll call that students. Those are all the students in the class. I've broken it down in exactly the way that we've said. All right? Does that make sense? What this table is going to look like? It's going to be the exact makeup. We've just pretended there's exactly 100 students. That made the math easy. Like there's the students table. If I show the whole thing, you see that there's half as many declared as undeclared for second year, second declared, second undeclared, and then there's a lot more third declared than third undeclared. Yeah. So there it is. And so, yeah, if I randomly sample, like students dot sample, give me like 10 of them. Look among the declareds. Is it more likely there to be a second year or a third year? Who knows? It's also random every time, so you can't really judge too much there. There's a third declared. There's a third declared. There's a second declared. Another third declared. Who knows? So we can do some math now. We can do a pivot. That would be nice. So I can pivot by the two things I have here. I can pivot by or these columns, so year and major. Capital year, capital major. This is like the simulation version of solving this problem, I guess. So let's put major on the, like whether or not they've declared a major on the X, and then year on the Y. And you kind of see how to solve the problem now, because we know that we're looking at declareds only. So like here's second declared, here's third declared. Do you see how there's only 30 second year declareds and 32 third year declareds? So just ever so slightly, if we were to pick randomly, we're more likely, if we know that they were declared, they said they're declared, we're in one of these, we can cross off these guys. We know we're in one of these. Just ever so slightly, it's more likely for it to be a third year now. See how that changed everything? So that's interesting. So we gained some new knowledge. We asked a question. We gained some new knowledge. Like, what was their major? And that shifted everything. Because like before, if I didn't know anything about that student that I randomly called on, they were more likely to be a second year, weren't they? Before I knew anything, they were more likely to be a second year. But the second I know something new, the second I gain some new knowledge, I ask them another question and they give me an answer. But the second I have this answer, it shifts everything in favor of it being a third year now, that random student. You see that? That changed it. That's interesting. So we wrote some code to find that. Are there any questions about how the code works, how we discovered that idea? So there's some math involved that we can do instead, and we should learn about the terms involved so that we can all talk about it with other people outside of this class. So the way to solve for this, the mathematical way, it's called using Bayes' rule. So we're discovering some probabilities, and it's after we've like asked another question, after we've gained some new knowledge, we've been given something new. So the word given is going to be important here because there's a symbol that gives us that. So yeah. Here's what we got. So our goal is we've got some new information, right? We've got some new information, and we want to use that to update our prediction about, like, was it a second year, was it a third year, or whatever we're trying to do. So we're doing a probability calculation, and we want to know, like, was it a second year or was it a third year, given that we know that that student has declared their major. That's what we're asking. Does that kind of make sense? So given that I have the answer for whether they've declared their major, is it a second year or is it a third year? Yeah, that's the kind of question I'm asking right here. And so here is the mathematical way of saying that. I want the probability, where capital P means I want the probability of something. Probability of was it a second year, because the opposite is a third year. Right? Probability of was it a second year given that they've declared their major. So that little bar there, it's like shift backslash. It's the thing above your enter key. This little bar symbol, you read it as given. So I want the probability that this random student is going to be a second year, given that I know that they've declared their major. You see how I'm reading that? So that's what we want. We can draw a little tree that looks like this, a little branching thing, a little diagram to help us, but there's still a formula that we need. So if we start with no knowledge, right, here's like the root of our, this is a tree diagram. I think it looks like the roots of a tree, right? So if you start at no knowledge, the base of the tree, the trunk, you can branch off, and it kind of tells you like what the makeup of the class is, what the makeup of like what you're trying to do probability stuff on is. So you read this as like 0.6 chance you can go this way, 0.4 chance you can go this way. So there's a 0.6 chance that you end up in second year, there's a 0.4 chance that you end up in third year, right? So that's the knowledge of the makeup of the class. And then you know that half of the second year, once they're in second year, you know that half of those are declared, another half are undeclared. So you see how I'm reading that diagram? And then if it was the third year, it was a 40% chance to get to the third year. But if you got there, then you know that 80% of those guys are declared, 20% are undeclared. Okay, so yeah. And so we want to know, what is the probability that we get a second year, we pick a second year, given that we know that that student has declared a major, all right? So that's this. Like, what is the probability that we get right here? Does that kind of make sense? That's the kind of thing that we're asking. We're not sure. We're not sure which one we're in. We want to know, like, what's the probability of us getting here versus maybe getting here? See that? It's like, given that they've declared a major, was it a second year or was it a third year? Which of these two declareds am I in right now? You see how I'm reading that? So that's how you read the diagram, and then now here are some terms. So when you don't have any knowledge, it's like before, the before times, prior means before, right? So the prior probability, before you have any new knowledge, is 0.6 chance, right? There's a 60% probability that you just randomly picked a second year with no extra knowledge. That's your prior probability. Before you get any extra information, you call that the prior probability of being a second year. Just the probability of being a second year is that, all right? So that's like P second year. That's what that is. It's 0.6, right? And then this right here is the probability. This is 0.5, right? That's the edge right there. So 0.5 is the probability of that student being declared, given that you knew they were a second year. You see how you can read that? Does that make sense, how you can see that? Like the 0.5, that this number right here means it's the probability of a second year student being declared. So it's the probability of seeing declared, given that you know you've got a second year student. See that? It's backwards to what we actually want. You see the difference? It's backwards to what we actually want. We want to know what's the probability that we have a second year on our hands, given that they've declared a major, given that we know somebody's declared their major. All right? Which means you got to start in both of these. Like, we're either in this one or that one. Like, what's the probability that it was this one all along? Okay? So that's how you split up your data. We know, right? The second you said that you've given somebody information, given that you know somebody's declared their major, you can immediately cross off the undeclareds, right? Because that, I know that's not true anymore. Given that I know somebody's declared their major, that means I'm in one of the two boxed things, the dashed one or the solid one. So we know that we're either in this one or the other one. Boop. So that we're in that one or we're in that one. So we know we're in one of these. Okay? And so the question is, what is the probability that we're in this one rather than that one? What's the probability that we've got a second year on our hands, if we randomly pick one, given that we know that that student that we've chosen has declared their major? That's a true thing. So they're not undeclared. Okay? So it's just kind of like it's the weight of this, it's the probability of that versus the probability of that, which one's bigger. All right? That's how we know it was a second year. So how do we get there? How do we get this one knowing both, right? Given that they've declared a major, what is the probability that they are a second year student? All right. So it's kind of like you take these ones, divide how many of these are over the size of like this one plus that one, kind of thing. Like this is your universe right now. You're either here or here. It's like, well, there are more of these or more of these. Like this size over this size plus this size. Okay. Because that's how we read this, right? It's like, how many third years are there over how many second year and third years are there that have been declared? Kind of read that in the same way as me. It's a little bit weird the first time you see it, but that's the kind of probability calculation we'd like to do. What is the probability that we get a second year student given that we know that that student has declared a major? And we know that's going to be smaller. It's going to be smaller than the probability of a third year student given that we know that that student has declared their major. Okay? So do the symbols make enough sense? Do the words make enough sense? Because now there's a formula. We can go to that formula. Okay? So we know the opposite probability, right? We know the probability, that's 0.5, right? Of there being a declared student given that we know that they were second year. So what's the probability that a second year student has declared? You can kind of read it backwards sometimes. A second year student has declared their major, it's 0.5. Right? What's the probability that you've got a declared major given that we have a second year student? That is 0.5. Okay? So you can kind of read it backwards. That's not what we want. We want it the other way around. We want to flip it. We would really like to flip it. And so here is Bayes' rule. So it was invented by a dude with the last name Bayes, I believe. That would only make sense. And here's the formula. If you want the probability of A given B, but you know the probability of B given A instead, and the probability of just A and B, you can do some math, and this rule comes out of it. All right, I will prove this rule to you in CSI 26 if you ever take that with me. Not here. We're just going to use the fact. So you can flip it with this formula. Probability of A given B is this. Probability of B given A times probability of A over the probability of B. That's what we get. Okay. So this might be a good formula to put down on your cheat sheet for the final, for example. Unless you can memorize it. So yeah, this is how you can flip it. You can use the other thing to get this thing. Okay? But you can also kind of read off this table the same idea. And so I'll show you it both ways. It's this is what we want. So following this formula, we want the probability that we've got a second year student given that we know that the student's declared their major. That's equal to, following this pattern, it's the probability that we have the probability that a student is declared given that they were a second year. So that's this one, right? We can kind of zoom out and get rid of those other ones again. So this one is 0.5. That's the probability that a student has declared their major given that they were a second year. It was half and half for second years. And then we multiply that by the probability that we have a second year on our hands. That's the prior probability. So that's 0.6 over the probability that a student has declared their major in general. All right? The probability that a student has declared their major in general. And so that's kind of the hard one for us to find together. Let me try to teach that to you. So the probability that a student has declared their major in general is just like this. Like, let's see. How do I want to say that? Dun, dun, dun. Oh, hey.
Check if I left my charger.
Oh, yeah, go for it. No worries. So we want to know the probability that a student has declared their major in general, which is kind of backwards to what we have. But there's ways to solve for it. So let me have us think about it in a little bit of a different way. First, we can multiply probabilities. That is possible. It is possible to multiply probabilities and get something. The probability that we have a second year student who has declared their major is equal to 0.6 times 0.5. because that's an and. Do you remember our original rules about probability? If you want to know two things at once, like the probability of one thing and another, you can multiply their individual probabilities. So the probability that we have a second-year student who has declared their major, we know both of those things at once. The second-year student has declared their major. It's 0.6 times 0.5. That's the probability that we get one of those. All right. The probability that we have a second-year student who has not declared their major is 0.6 times 0.5 as well, because it's the equal amounts. So that's like, yeah, there's a 30% chance that we've got a second-year student and they've declared their major. You see how that's kind of, it's split it up into like all of these. You count them down here kind of thing. This was our, if we think about the counts, that's probably useful. So there were, in a student, in a group of all these students, you had 30% because we used 100, right? 30% were declared second years. 30%. 32% were declared third years, right? That's 32%. We know that, given just the math we did in the simulation. 30% were second year undeclared, sorry. 30%. Did I do that backwards? I don't remember. Yeah, 30% undeclared, that's fine. And then 8% were third year undeclareds. So those are percentages, and you can calculate these percentages by multiplying these ideas. So 0.4 times 0.2, that really does give you 8%. Does that make sense? That really does work like that. That is just a mathematical factor. You want two things at once, like a third year and they've declared. What's the probability in general of the whole class? That's 0.4 times 0.8. That will be 0.32, 32%. Probability that we've got a second year and they've declared their major out of the whole class. That's 0.6 times 0.5. You've branched off twice. You can multiply those probabilities and get 0.3. Same with the other way because it's also 0.5, also 0.3. So hopefully that proves to you that rule is true. And so that will help us know, like, what is the probability that we've got declared on our hands, right? Out of all the students total, that is, what's the probability that we've got declared on our hands? Well, it's 30% plus 32%. Does that make sense? It's just like, that's the probability that we have a declared student at all anywhere, either second year or third year. It's 30 plus 32. That's 62%. So that's 30% plus 32%. Another way to calculate that is to read it off the table. You do like 0.6 times 0.5 plus 0.4 times 0.8, because that's how you calculated those percentages. That's how you can do that. All right. So that is 0.6 times 0.5 for that 30% plus, how do we get to this 32? 0.4 times 0.8. So that's how you get the total percentage of did anybody at all ever declare their major, okay? So that's how that works. And that is about, if we do the math, that's the same as this, right? It's this is going to end up being like, what's the probability they've got a second year given that they've declared their major? It's 30, right? 30 is the number, like that's the percentage, like that's how many there are, right? 30 second year declared students over the total number of declared students, so 30 plus 32. That's another way to calculate it. I hope you see that. 30 plus 32. That was our simulation-based way of doing that. So what's that number? It's going to end up being the same as this number, though. What's 30 over 30 plus 32? It's like only the declared students, set probability of being a second-year declared students, 30 over the size of all of those, the number of all of those. And so it's about 0.48, so 48%. And you better believe 1 minus that is the probability of being a third year, given that we have a declared student, 0.48. Yeah, I think that's most of what I wanted to say. Is that right? So if you do this math for the same reason, that's going to be, this is now on the top, it's 30% over 30% plus 32%, which is just all this, just like shifted over a little bit. No big difference, all right? 30% over 30% plus 32%. It's kind of a way to think about it. So yeah, so that's the formula. I'm not going to prove to you why the formula works, but that's how you use it, and hopefully you can see pieces of it and why they go together. Are there any questions about that? You see it? So the probability was, you got a second year on hands given that we know they've declared their major. This formula checks out, and you can think of it in this way as well. It's just like, all right, what's the probability that we have the thing that I want, that we're here, Just like the probability of that, given that we've crossed out everything else, it's like 30% over 30% plus 32%. Like that's the declareds only, just weight them in that way. So that's how you solve for it, and that's why we get 0.48. We've just kind of crossed off everything else. There are 30 versus 32%. That was it. That was our universe. We can cross off all these guys because we knew that student was not undeclared. We knew that they were declared. That was what we were given. Okay, so it's a bit of a weird formula, but I just want you to know how to use it. Any questions about any of that example? Hopefully you can follow it. Yeah, so I want to show you another one. I want you to try the same thing. I'll give you the formula. I want you to try to come up with the number. You can use Jupyter to do the calculation. It's a weird one. But here's the setup. Here's another exactly similar kind of tree diagram. And it has to do with like tests for a disease, like COVID or something. So let's say we've got a test for a disease, and it's a very rare disease, right? Test for a very rare disease where only 0.4% of the population has that disease in the wild. If you go get a random person on Earth, 0.4% has the disease. 99.6% of the people don't have that disease. It's a very rare disease, all right? So prior probabilities, disease versus no disease, are those. But, and then we have a test, right? We have a test for each of these different kinds of people. They're going to take a test for that disease. If they ended up having the disease, if they really had the disease, this rare disease, the test works pretty well. The test works quite good. They are going to test positive, like they should, with 99% accuracy. You see how I'm reading that? If they had the disease, the positive test was 99%. So this is the probability of a positive test given they had the disease. That's 99%. Okay. The probability that they got a negative test, like the test said negative, even though they had the disease, so the test got it wrong this time, there's a 1% chance of that. Okay? There's a 1% chance of that. Unfortunately, tests are not perfect. There's a 1% chance of the test failing and saying that, no, you didn't have the disease, even though they really did. Okay? And then, for the people who did not have the disease, the test is really good. It says with a 99.5% chance, they're going to get a negative test back given that they did not have the disease, which is perfect, right? Because it should be saying no for them. They didn't actually have it. Okay? But also, for that group, sometimes the test lies again. Sometimes they get a positive result back with 0.5% chance, even though they didn't have the disease. So those are the 4 prongs of the end there, and I hope you see how you can read that. So that's what's going on there, and we would like to know, like say you got somebody random, like you pick some random person on Earth, and you test them, and their test comes back positive. So they get a positive test. The question for you is, how would you classify them? How would you say, what would you give them? What's more likely? You know that they got a positive test result, so you know that you're here, right? Would you say that they have the disease? Or is it more likely still that they did not have the disease? It's a weird question to ask, but you can try it with this formula in mind, all right? So, yeah, you're trying to do this. You're trying to find the probability of, was there a disease given that the test was positive, all right? So you don't have to post this anywhere, but let me give you my examples here. Let's see. Is there any easy way for me to give that to you? Not really. Let's see. Yeah, I think I'll give you that in the formula. I think that's all we need right now. So take a couple minutes to discuss, see if you can figure out this probability. Probability they had the disease given that the test was positive. Okay? Because that's what we'd like to know right now. Given that the test was positive. Try to set it up at least. Like what are you trying to find? And remember that you have a lot of these things backwards. Like what's the probability of the opposite of this? What's the probability that you got a positive test given that there was a disease? That's the 0.99. You see that? Given probability of a positive test given that the people, the person you're testing had the disease, that's 99%. You want the opposite of that. All right, so it's like, which one was more likely? I guess is the question. This one or this one? All right. Try to calculate the number. And even if you don't calculate the number, you should be able to say disease or no disease pretty quickly. Which one is more likely? Just go and find like which of these is more, which of these is a higher probability, this one or this one. Does that make sense? Just in itself. And this number is going to give you that in some way. Okay. So think about that. It's useful to think about that. That's so fun. You don't have to post this anyway, but I want you to try at least to do some of the math. Because you can figure out the probability of a positive and there wasn't a disease, and also the probability of a probability of positive and there was a disease. They didn't do that. That's the multiplication. That doesn't give you the actual final probability that you want, but it will tell you which one's more likely. I do not know. Maybe another minute to try it, and then we'll do it together. Mm-hmm. All right. Any brave souls want to say which one you would give, like if you were the doctor? Would you say they had the disease, or would you say they didn't have it? This is a little. I wouldn't have this question if it was a normal answer. So you're actually going to want to tell these people, this person that you took randomly and got a positive test for, it's a better idea to tell them that they didn't have the disease. Actually, it's really weird. But let's look at why. We could very quickly say disease or no disease by just seeing the relative weights. Like, what's the probability that this random member of the population got a positive test and they actually had the disease? That's 0.004 times 0.99, right? Probability that both of those things are true. That's 0.004 times 0.99. That's 0.396%. This is a very small percentage, but still. But then we know that their test is positive. So what's the other one? What's the other option? They were here, right? So what's the probability that they didn't actually have the disease, but that test for them was positive? So that's going to be 0.996 times 0.005. Did I do that right? Yeah. It looks, then that's 0.498%. This percentage is higher than this percentage. Does that make sense? This tiny percent is still small, but this tiny percentage means that it's more likely that you randomly ended up in this state, given that you knew that there was a positive test. Okay? That's so cool. That's so weird, right? You're going to tell them that they didn't have the disease. And that's going to be your answer. Crazy, right? Disgusting. And so if we want to do the actual calculation, it's just like if you think about it, it's going to be this over, like the probability, if this is your universe, like these need to add up to now 100%. Like this carries this much weight, this carries this much weight, but they're now, like those are your only two options. They must add up to 100. So it's essentially going to be this over itself plus the other one. That's kind of how you do it. And you will get that out of the formula, more or less. So we want probability of disease given that we got a positive test, that's equal to, so we want the probability of, do we have a disease given that we have a positive test, that's equal to the probability, the opposite, the probability that we have a positive test given that they had the disease, times the probability that there is a disease, they have the disease in general, over the probability of how likely is it to have a positive result. Okay, that's how you can do it. And so the numbers are going to be probability that positive result given that there was disease, that one, 0.99. Probability that there was a disease at all is 0.004. And then the probability that there was a positive result for anyone in general is just like, what's the probability that you are here or here and not the others? Yeah. Like what's the total weight of you being here or here? That's just like this times this, that'll get you here, plus this times this, that'll get you there. That's that full probability that we were anywhere that was positive. All right? Because we divide that by 100% and the rest added up to 100, so that's fine. That's fine. So that's going to be, probably that was positive at all was like, all right, 0.004 times 0.99. That was this way of getting positive, plus 0.996 times 0.005. That was this way of getting positive. And so I hope you see that this is part of the bottom there. That's how you can think of it. It's like it's like the relative weight of this one versus anybody else. There was only one other option here for our example. Sometimes there's more. So it's just like this over this plus this. That's kind of what we just did. So just to spell it out, we're doing this guy over itself. Like, what are all the other ways for it to be positive? That could have been that way with that percentage or this way with this percentage. It just kind of like rescales everything to be over 100%. So it looks like there's about 55% chance it was the case where there wasn't actually a disease, but we wanted to know, was there a disease? So it was really this one on top. That one on top over the sum of all of them, which involved that one first. So let's just do it in that order. There's no real difference. So that's another way to think about it. All right, and it'll be 0.44, so about 44%-ish chance that you had the disease given that you got a positive test result. So it's more likely that you didn't actually have the disease, even though you got a positive test result, which kind of means that even though this like test looks good on paper, right? 99% chance you got it right. When there was a disease, 99.5% chance you got it right when there really wasn't a disease, just due to the fact that the disease was so rare, like this. The fact that the disease was so rare still means it was more likely for the test to be an error for that person. It's crazy. Any questions about that? So Bayes' rule lets us just quickly have a formula for calculating what's going on. All right. So let's see here. We can do a simulation of this as well, just to show it to ourselves. We've got time. And so here's how we can do it. We can say, all right, let's make a population of, I guess, what are our percentages? We got thousandths. So maybe we should have a population of 1,000 people so that there's always even numbers. Is that going to work? Yeah. Let's do that. So let's say, like, all right, the number of people that have the disease, or the disease is true, is going to be 4, right? 4 out of 1,000. So that's going to be your probability that there is a disease. Let's call that prior probability of there being a disease. that's going to be 0.004. So the number of people that actually have a disease then is going to be that probability times like a number. So let's say we've got 10,000 people, because then all these numbers become even. I'll make actually 4 people, right? Right, times 1,000. You can do a bigger number, that's fine as well. But there's that. So like the number of people that have the disease, then there's 4 of them. Does that make sense? Like we can do that kind of simulation. And due to the way we're going to do this kind of thing as well, unfortunately, you cannot make a bunch of things in a list when you have a float like this. Like this is a float, not an even number, so that's 4.0. Can't do that like times the list high. That will give me an error, but like 4 times the list high will give me 4 highs. Like I know this is going to be even just due to the way I'm doing the math, but we need to tell Python it's going to work out. So we have to say int. Give me an int, please, out of all that. So that'll make it the 4. It'll chop off the decimals if there aren't any, but we know there won't be. All right. That's the number of people that have the disease. The number of people that don't have the disease, no disease, ND for no disease, is the same idea. It's going to be just like we have 1,000 people, subtract the number that had the disease. Yeah. That's the number of people that don't have a disease. 996 at 99.6, right? So we can calculate that easily. It's just like 1 minus the other option. And then, all right, let's say now we need the others, right? We need these other probabilities, like the probability that we have a positive test result given that we had the disease. Dun, dun, dun. So that's the number. Let's turn this into actual numbers with our simulation. The number of people that had a positive result given that they had the disease is 99% of the diseased people, right? So 99% times the number of diseased people, which was 4, times ND. I think I'm going to have to use bigger numbers now, darn. Because that number I can't use and make it whole, unfortunately. 3.96, oh no. So yeah, I need another 2 zeros then, because then it could be 396. Let's do it in that way. So I need another 2 zeros. That means I need a population of 100,000. All right. So let's pretend that we have a population of 100,000 instead, because that will make everything work. So that means now we have 400 people, right, out of 100,000. 400 people that had the disease. That means we had 600 that, no, sorry, it's out of 100,000. 99,600 people that didn't have the disease. There we go. We multiply by 100,000. And now we get a whole number for this one. Number of people that had a positive result given that they had the disease. Exactly 396. And we can make that whole so that I can multiply that by list things to do our simulation. Int version of that, please. So that'll work. We do the same thing. Let's the number of people now that had a negative result given that they had the disease. That was the 0.001, the opposite, right? That's the opposite. Another way of thinking about that was like, take all the people that had the disease, subtract those people that had a positive test. So that's the number of people that had the disease minus the number of people that had a positive result on that, given that they had the disease. That will give us the negative result people, given that they had the disease. And I think, is that going to be most of it? That's that one. Positive D, negative D. Let's also do the number of people that had a positive result, given that they did not have the disease, no disease. That's 0.005 of the people that had no disease. That's exactly the same idea. 0.005 of the people that did not have ND now. I hope you can kind of see where I'm going with all these numbers. But we're just like simulating a population where we can get whole numbers out of the deal, like actual people and counts for those people that were in each category. And then the same for the number of people that had a negative result, given that they did not have the disease, is, well, you can do the same game, or you can be like, oh, it was just the number of people that did not have the disease, subtract the number that had the positive result from that. And you get the number that had the negative result. So that is ND minus N pos ND. Number of people that didn't had a negative result subtracted by the number of people that had a positive result given that they had no disease. So there. I think that I said, yeah, there were people that did not have disease. That was the first thing. And all right, I think we're good. So now we can make big long arrays of things. Like they can like how are these people doing? So we have how many diseases and no diseases? We have ND diseases. Disease times ND. And we had how many no diseases? No disease. We had N and D of those. There we go. So that's like the condition of the people. Do they have a disease or do they not have a disease? And then let's see what we want to do. We want to know next, like, all right, among the disease people, how many was the positive test for? How many was the negative test for? Then how many for the no disease people? How many positive? How many negative as well? So if we just go in order, it should line up for the like what was the test results for those people. It was all right. We got positive for the first few diseased people, right? Times that's this one positive given that they had disease, plus negative repeated a bunch of times for the people that had the disease as well, times number of negative test for the diseased people. So that'll cover all the diseased people. That's their results. Plus, we want to do the same thing for everybody else, for all the people that did not have the disease. That's times, I guess I need to do this on 2 lines maybe. The test results for the diseased people were those. Then we can do the test results for the no disease people. ND, I guess. D and ND maybe. Was this, how many positives? This many positives. That's a little complicated. And then how many negatives? This many negatives. And this will add up to the 100,000 again. Like those test results we can append to each other. So we got to make arrays out of these. np.array, that, np.array. It's hard work doing a simulation. np.array, that. But I hope you see what I'm doing. Just like making concrete counts of people for which all these things are true about them. So if I combine those together, that's our like our test results. In total, it's np.append those 2 ones. This one, bless you. And then this one too. Which took too long. So like, what's the length of all these people? Diseases and no diseases, condition. 100,000. What's the length of test? All the, like, what were their test results? 100,000. So I've got a label of disease. I've got the label for positive and negative now. And I can make a table for these people, finally. Like, T is a table that has 2 columns. Like, what was the condition of this patient? Do they actually have the true condition? Like, did they have the test? Did they have a disease really, or did they not have a disease really? And then, what was their test result? What did the test say? Did it agree with their true condition? And so that t.sample 10 or something, so you can see what's happening. Oops. Oh, sorry, with columns. So it's so very likely, unfortunately, when you take a sample, that it was no disease and negative. Like, that takes up the bulk of all these people. But I hope you can kind of see what's going on there. For everybody, I just got a bunch of disease positives, then a bunch of disease negatives, then a bunch of no disease positives, a bunch of no disease negatives. I've got as many as I need to make this work out. All right, so that was the labor of love that I made for this diagram. And so we should see if we do a pivot on this table T now. Pivot on test result, and then true condition. Let's do it in that order. I'm going to take a second because it's a big table. There it goes. So, okay, this is exactly what we wanted. The if they had the what was it? If they had a positive result, we know we're here, or in one of these, and it looks like if we had 10,000 or 100,000 people, 498 of them had no disease. 396 of them had a disease. Does that make sense? So that's how you can simulate it, just like giving actual numbers and making them whole. Here we noticed we needed 100,000 people to do like a simulation. We made a 100,000 sized table. It was quite large. Any questions about that? It's just like simulating the math rather than actually doing the math. They both work. So you probably tell this random person that they don't have the disease and send them on their way and they'll be happy, right? But we should also think about this from a doctor's perspective, because like maybe you are going to do medical data science or something. If a person, like the person taking the test is not a random person, are they? They're probably somebody coming into the doctor's office thinking that they might have this disease, yes? So maybe they have some symptoms. Someone coming to that doctor's office asking for a test is not being picked at random at all, right? Not at all. And so you can come into the idea of a subjective prior in that way. So a prior probability is like what we know about disease or not disease likelihoods before we notice anything else about the test results. You can fudge the numbers a little bit if you're a doctor. Like suppose the doctor's subjective opinion is that now there's probably a 5% chance that somebody coming into this office wanting a test for this disease, there's not just a 0.004% chance, or sorry, 0.4% chance that they had the disease. There's probably like a 5% chance they had the disease. It's more likely they have some symptoms, they think they got a family history, who knows, right? The doctor's subjective opinion. So the doctor is injecting a subjective prior into this diagram now. I think that there's like a 5% chance that the patient had the disease. That will change everything. Now there's a more likely chance that we were in, more likely chance that we're in this one versus this one. I hope you see that. All right, that's going to change everything. If you do the math, let's do the math ourselves here. Whee! Instead of all this, because it's the same calculation, right? But now it's 0.5 for the probability of there being a disease at all. Boop. So instead of this, it's going to be, that is 0.5. Or 0.05, sorry. 0.05, and then these change. Now this is going to be 0.05, and this one has to equate it, so it's 95% chance for the other one. 0.95. And so the likelihood, if you just do it, it ends up being a 91% chance now that that person really did have the disease. The second you fudge these factors to say that, no, maybe they probably actually were coming into the office because they're more likely. They weren't randomly picked. They're more likely to actually have that disease. Okay? So that's kind of fun to think about. And we can do that math as well in the simulation. Be like, all right, that's why I use this first variable. We do this all over again and do a pivot. Boop. We say that the prior probability of the disease is 0.05 now. Subjective prior. Now it's more likely that if they have a positive test result, like much more higher chance that they were actually having the disease rather than not having the disease. In that case, it's just like the doctor making up numbers, but it really wasn't a random choice of a person. It was somebody who thought they might have it, and so that increases the numbers a little bit. And so, yeah, it's just like, it's kind of made up in a sense, but it's subjective, not objective anymore. But the math still checks out, and we can do it and discover things together. So, yeah, I think that's the moral of the story. Sometimes you can change the numbers if you think there's a good reason, and that will change your outcome quite a bit. Yeah. Any questions about any of that? You can do that simulation. Your book made a function to do both of these at the same time. It took prior probability as an argument. I'm fine with not doing that. But yeah, that was the chapter, and I think that is most of what I wanted to say. Are there any questions about anything we talked about today? So that was updating your predictions based on new data. Like given some other thing, given that I knew that student told me that they've declared their major, that changes the setup of things. Given that I know that there was a positive result, that changes the outcome, the likelihoods of things. So yeah, that's chapter 18 in a nutshell. That's the last one in the book. So if we are good, do yell at me if we're not. These are the last two assignments I can assign due dates for. So let's do that. We've got homework 12 and lab 10. Dun, dun, dun. Let's see what's on the schedule. The last day I can make something due is going to be next Friday. And so I know you have project 3 due next Friday, but we're probably going to have to double up that, just like get everything in by then. So yeah, I'll make at least the first one. Let's do homework 12 due on the Wednesday, and then I'll have lab 10 due on the Friday. Like the 5th is the last day to turn in anything as well, at all, and we'll talk about that next week. But that's the last day of classes, the Friday. So we gotta place everything due then. So hopefully you've already started on project 3. But like that'll be a Wednesday assignment and then a Friday assignment. Okay, that'll be when they are due. And I think that's everything for chapter 18. Any last thoughts we want to discuss before I stop the recording? All right.